Anyway, the point of this is 10 to the minus 21 is an extremely small number, right? I mean, could you even measure that? 10 to the minus 21 joules? No. And so, is this an appropriate number for kinetic energy? I mean, the temperature is 25 degrees C. And so it turns out that maybe. I mean, if gold was what, 30 times 10 minus 23, or 10 to the minus 22, 2 times 10 to the minus 22, we could probably get 100 gold atoms in 10 to the minus 21 grams, right? Something like that. 50, 100. Couldn't even see it. But this is significant because even though this is tiny, this is the average kinetic energy of what? This is joules per. Avogadro's number is typically 6.022 times 10 to the 23rd what? Per mole. Molecules. I can cancel out the molecules here. It's joules per molecule. And so this is the amount of kinetic energy on a single molecule. Well, you know what? This is a significant amount of energy for a single molecule. Yeah. And so it depends on the scale of what we're looking at, you know. If we're looking at it on a macroscopic scale, 10 to the minus 21 grams of gold is absolutely nothing. I mean, if somebody said 100 atoms is nothing, right? Couldn't even see it. But at an atomic level, you know, 10 to the minus 21 grams is significant at an atomic level. And you're looking at individual atoms. And so this is joules per molecule. And so we can figure out the speed of these. Now, are the speeds going to be the same? You know, the kinetic energies are the same, but will the speeds be the same? We're just going to look at one speed in that distribution. What's the one speed we're going to consider? The RMS speed. It's the most important. The effective speed. And so this speed, will it be the same? Are these molecules going to have the same effective speed? The answer is no. They don't. There are two ways. We could have gotten the kinetic energy. You know, this is the most direct way of getting the kinetic energy. We just figure out the kinetic energy based on the temperature. Another way we could have gotten the kinetic energy is by first solving for the RMS speed. Once we get the RMS speed, then we can solve for the kinetic energy using this equation here. Likewise, for getting the speed, we have two ways. One, we could just solve this equation here, or two, we can use the kinetic energy and solve it using this equation here. So there are multiple ways of solving these problems. Either one's okay. And so if I want the URMS speed, well, you know, I could get it from here, or I could get it from here. Which way do you want to do it? We should maybe do it both ways, should we? right, so these are the basic calculations we're going to do in kinetic molecular theory. So we calculated the kinetic energy, which I erased, and then we have the URMS speed. And so URMS speed, well, let's go ahead and get that. URMS speed we can get either from this one, square root of 3 RT over the molar mass, or this one. So we rearrange that equation, we take the square root of E bar K, it's 1/2, so 1/2 mu squared. And so we have to E bar K divided by M, and then 1/2, it'll be 2. Is that right? So rearranging that other equation, yes? Okay, so let's go ahead. We already have E bar K. We just need the mass. And so let's go ahead and do this. The reason these aren't going to be the same is because of this. They weigh different amounts. And so if I want the speed of O2, then the URMS of O2 using this equation is going to be the square root of 2 E bar K. What was E bar K again?
6.17 times 10 to the negative 20.
It was 10 to the negative 21.
Yeah.
And what were the units on that?
Joules per molecule.
Joules per molecule. Okay, and then what is the mass of an O2 molecule? The mass of an O2 molecule, we'll just take the average mass. The average mass is going to be 32.00 what? How much does an average oxygen molecule weigh? .00, not grams. How much does a single average oxygen molecule weigh?
You could divide that by
We could, but it's much easier just to go direct. A single oxygen on average weighs 32.00 U. Each oxygen weighs 16 U, 16.00. Well, the units aren't going to work out, are they? Right. And so what units do I need? This is U per molecule. Oh, molecules cancels out. Molecules cancel out molecules. Well, it's based on the joule. You know, what is a joule equal to? A joule is equal to a, yeah. So we have kilograms meters squared per second squared. And so we want this not in terms of U, we want it in terms of kilograms. So we just do some dimensional analysis here. Because we know in 1 gram there's 6.022 times 10 to the 23rd U. And then there are 1,000 grams in a kilogram. Okay, so the U cancels, the grams cancel, the kilograms cancel. And we're left with meters per second squared. Well, if we take the square root of meters per second squared, we end up with the units meters per second, which is a speed, you know, how fast it's moving in meters per second. And so let's go ahead and calculate this and see what the URMS speed for oxygen is.
6'8", 5'19", 188, 28.
6'8", 5'19"
Yeah,
times, oh,
that's it.
68,519. 68,519 meters per second. That's a little bit on the high side. Did other people get the same answer?
Not two.
Yeah,
Or do you do 2 times that?
2 times that.
Is that just in the?
Yeah, because I solve for URMS here. E bar K is equal to 1/2 MURMS squared. So solving for URMS, I multiplied both sides by 2 and then divided by M. And then took the square root. And so I get 2 E bar K divided by M root. That's equal to URMS. So that's where I got the equation from. So it's 2 times the average kinetic energy.
And the average kinetic energy is 6.1.
Well, yeah, that was from the previous calculation. Maybe we have to double check that. But you know what? There's an alternate way we could get URMS. So let's just go ahead and calculate it. Both ways give us the same. That's right. URMS is equal to the square root of 3RT over the molar mass. And so let's go ahead and plug this. This is going to be for oxygen. 3 times R. R is 8.3145. We're going to use the units. Kilograms, meters squared per second squared. Here's joules. Times T, 298 Kelvin. Actually joules per mole Kelvin. Divided by the molar mass. The molar mass is going to be in terms of kilograms per mole. And so in terms of kilograms per mole, oxygen would be 0.03200 kilograms per mole, or 32 grams per mole. We'll take the square root of this whole thing. So moles cancel, kilograms cancel, Kelvin cancels, and that leaves us with meters squared per second squared. And so this should give us the speed, the RMS speed.
$481.96.
481.96 meters per second. Sometimes it's hard to visualize meters per second because we're not so used to it, but let's do this in miles per hour. And so in terms of miles per hour, there would be, how could we convert it? So we go from meters to centimeters. Let's do that. So 100 centimeters per meter. And then we'll go from centimeters to inches. So an inch is 2.54 centimeters. And then we'll go from inch to feet. Foot is 12 inches. And then we'll go feet to miles. So there's 5,280 feet in a mile. That's miles per second. And then we're going to go to hours. So there's 60 seconds per minute. And then 60 minutes per hour. And so this will give us the miles per hour that the oxygen's moving, or the oxygens are effectively moving. And so how many miles per hour is that? What do you get?
1,078 measurement.
Yeah, 1,000, what is it? 1,000? 1,078 miles per hour. That sounds right. I think that should be about right. And so the oxygen's moving at 1,000 miles an hour. Do you think it's going to have collisions? Yeah, it's going to have a lot of collisions. So the thing about the collision frequency is slightly off. It has lots. lots and lots of collisions per second, okay? It's moving fast. All right, we'll continue these calculations. These are the basic calculations. We'll look at some other stuff. Stop here.